If you recall back a few videos, we talked about the idea of congruence of shapes, and we defined it based on rigid motions and the fact that the shapes would have the same size and shape. And we said, hey, if we want to see if two shapes are congruent, what we need to do is we need to figure out if there are a series of rotations, translations, and reflections, those rigid motions, that would take one shape and map it onto the other. Well, in this video, we're going to take a look at specifically triangles and how there might be maybe a few shortcuts that we could use that would prove that two triangles are congruent without having to go through the process of figuring out those rigid motions that would map one to the other. And we're going to learn about two of those shortcuts. One of them is called SAS, and you can kind of see what the SAS stands for right here. And the other one's called SSS, and you might be able to figure out what that stands for as well. And then we're going to learn about another theorem that has another kind of acronym name called CPCTC. We'll learn what those letters stand for as well. So let's jump right in and look at the first of these three theorems that we're going to be dealing with. It's called the side angle side triangle congruence, or sometimes just called SAS. And it says that if two sides and the included angle, we'll talk about what that means in just a second, if two sides and the included angle of one triangle are congruent to two sides and the included angle of another triangle, then the triangles are congruent. Then the triangles are congruent. So let's talk about this phrase, included angle. You'll notice over here I have a couple triangles, and I have segment SR marked congruent to segment XY, and segment ST is marked congruent to segment YZ. So there's my two sides. But then you'll also notice that where those two segments intersect, vertex S of the triangle, that angle, again, it's the angle where the sides that are congruent intersect, or sometimes you can think of it as the angle that's made by the two sides that we've kind of decided are congruent to sides on the other triangle. That angle is called the included angle for these two sides. That if maybe you can think of it as if I draw these two sides, or if I were to highlight those two sides, let's go ahead and do that. I'm going to highlight those two sides. I've included, in my highlighting, I've included angle S. So we can think of that as called the included angle. And if I do the same thing over here, if I highlight those two segments again that I've kind of said are congruent to a couple segments over here, by highlighting those, I'm also highlighting, or I'm including angle Y. So angle Y would be the included angle for these two sides. And so since I have the hypothesis of this big long hypothesis is true over here, the two sides of this triangle and its included angle are congruent to the two sides of this other triangle with the included angle, then I can say that triangle RST is congruent to this triangle over here. Now I have to be careful when I make these what are called congruence statements. When I write out these congruent statements, I want to write them out with paying special attention to the order that I'm going to put these letters in right here, because I need to do it in a way that shows that if I were to map this triangle to this one with rigid motions, that the R would go to whatever letter is named first here, the S would go to the middle letter in this name, and the T would go to the third letter in this name. So I got to think, okay, if I were to do that rigid motion mapping, what is R going to go to? It would go to X, the S would map to Y, and the T would map to point Z. Now, some of you are going to be able to figure that out by, in your mind, kind of taking this and doing the reflections, translations, and rotations that would map it to this. But if you can't do that, just look at the way that we've marked certain parts. For instance, I see that S is the angle. Angle S was the angle that we're using in SAS. And so an angle Y is the same angle. So the S and the Y should be in corresponding places in the names of the triangles down here. And then at the end of the other end of the shorter side with two line markings, I have R. And at the end of this shorter side with the two markings, I have X. So R and X correspond. And that leaves T to correspond with Z. I could have used a different name for triangle RST. I could have perhaps called it TSR. Let's go ahead and let's maybe say I'm going to instead call this triangle TSR. Then when I name the other triangle, I'd have to say ZYX, again because I want the T and the Z, the S and the Y, the R and the X all in the same places. So that is called the SAS triangle congruence. Next we're going to learn another theorem. It's called CPCTC, and this one says if two triangles are congruent, then each pair of corresponding angles, I'll start with sides, each pair of corresponding sides and is congruent, and each pair of corresponding angles is congruent. Okay, what is this saying? Let's think about what this is really saying in kind of everyday language. Well, if I had already told you that these triangles are congruent, and I give you given information that says triangle ABC is congruent to triangle XYZ, then each pair of corresponding sides would be congruent. In other words, segment AB and segment XY would be congruent. So I could mark segment AB congruent to segment XY. I could say that segment AB is congruent to segment XY. That's one pair of corresponding sides. It says, though, each pair of corresponding sides is congruent. So I can keep going. I can say that segment BC and segment YZ are congruent. Segment BC is congruent to segment YZ. Again, I can see that BC is the second and third letter here, YZ, second and third letter here in this statement. That tells me that they correspond to each other. This theorem says that, well, that means they're congruent if the triangles are congruent. Segment AC and segment XZ would be congruent. Segment AZ is congruent to segment XZ. But it also says that the corresponding angles would be congruent. So I could say that angle A would be congruent to angle X. Angle A is congruent to angle X. I could say that angle B is congruent to angle Y. Angle B is congruent to angle Y. And then I could say that angle C is congruent to angle Z. So the theorem says that when the triangles are congruent, then each pair of corresponding sides, that's all the information in blue, is congruent, and each pair of corresponding angles is congruent. That's what we wrote down here in red. So a lot of times this is referred to as CPCTC, and it stands for corresponding parts of congruent triangles are congruent. Corresponding parts, which means the corresponding sides and the corresponding angles, the parts of the triangle, corresponding parts of congruent triangles are congruent. And you may be asking, well, when would we use something like this? We should be looking at a picture up here, like what we had up here for this previous theorem, and then maybe it says in the on the picture that segment RT is 8, and it asks how long is segment XZ. So first, the thought process would be, well, I'd say these two triangles are congruent because they have two pairs of sides and the included angles congruent. So the triangles are congruent by SAS. And then once we knew the triangles were congruent, we'd be able to say that segment RT should be the same length as segment XZ. So segment XZ must be 8 units long. And that's what we would use this CPCTC for. All right, one more theorem that we're going to talk about in this video. It's called the side-side-side triangle congruence. So SSS stands for side, side, side. And this one's pretty straightforward and easy to understand. It says if three sides of one triangle are congruent to three sides of another triangle, then the triangles are congruent. And the triangles are congruent. And so we see in this picture here, we see a triangle here with segment AB congruent to segment ED, segment BC congruent to segment FE, and segment AC congruent to segment DF. All three sides of this triangle are congruent to the three sides of this triangle. According to the side-side-side triangle congruence theorem, then triangle ABC must be congruent to triangle, now again we got to think carefully about our name here, we went A, B, C. So we started at one end of the one tick mark side, went to one end of the two tick mark side, and then went down that side. So I think that means we start at D, go to E, and then up to F. So we got to call this other triangle DEF to show what parts can correspond to what. But that would be true. Triangle ABC would be congruent to triangle DEF because AB is congruent to DE, BC is congruent to EF, and AC is congruent to DF. So all three sides of this triangle are congruent to the three sides of this triangle, making the triangles congruent.